Welcome. This is the seventh video in our series on patterns among the primes, in which we study the cycles of gaps in Eratosthenes' sieve as a discrete dynamic system. In this episode, we'll look at models for constellations of gaps. This is a graph of all the gaps from 2 up to 82. We took our initial conditions from the prime 37. That's over there on the right-hand side, and the system parameter is 1. And then as Eratosthenes' sieve continues and the primes grow, the system parameter lambda goes very slowly to 0. And these are the relative populations amongst those gaps. We saw for gaps, if we can look at the cycle for a prime p sub 0, then for all gaps up to this bound, 2 times p sub 1, 2 times the next prime, we can identify the exact models for the populations of that gap across subsequent stages of the sieve. And that bound 2 times the next prime, that comes from one of those critical observations that the shortest distance between fusions is 2 times next prime. Once we had the linear system, then we looked at the eigenstructure, and we saw that the spectrum was dominated by the product of primes minus 2. So the dominant eigenvalue for the system is the product from P1 up to Pk of prime minus 2. These populations are all super exponential, so what we did was normalize and factor out that super exponential growth. We take that factor of prime minus 2 and divide it away. We get the system for the relative populations of gaps, the exact populations relative to each other. Same eigenstructure analysis. Now the spectrum has dominant eigenvalue 1, so the system converges. And that subdominant eigenvalue, product of q minus 3 divided by q minus 2, that becomes that system parameter. Starts at 1 and then goes slowly to 0 as the primes increase. These are those models of the relative populations of the gaps from 2 up to 82, and they group into these families by their prime factors. What we next did was take a section of these graphs, here shown at lambda equals 0.25, and we compare that section, shown here at the left, with data samples among the intervals of survival, among the squares of primes for those. So here, this was the sample where we have 14 intervals of survival, total of 31 million gaps, and we see that their relative populations of the gaps they conform to the models to first order. So what we're going to do now is follow the same analysis for constellations of any length j. So we'll first derive the population models. Those will still be super exponential. And so we will normalize those population models to get the relative population models. And then we'll compare those relative population models to data samples from the intervals of survival. To derive the exact population models for constellations, we look at constellations of length j and their driving terms up to length, say, j sub 1, and their span has to be less than that bound 2 times the next prime from where we got our initial conditions. That bound is important because it guarantees there is at most one fusion per copy of the constellation or a driving term. The Markov model is similar to the one that we derived for gaps. In each stage, there are j plus 1 boundary fusions. A boundary fusion eliminates a driving term or a copy of the constellation itself by fusing together those elements. Interior fusions promote a driving term to a shorter driving term. And then there's the remaining replication factor. How many copies survive the replication in step R2 of the recursion and the fusions in step R3 of the recursions? We again look at the eigenstructure. It's the same left and right eigenvectors. The right eigenvectors are an upper triangular Pascal matrix of alternating sign. The left eigenvectors are an upper triangular Pascal matrix. So the products telescope and we end up with a very simple diagonal matrix for the eigenvalues. The spectrum now is dominated by this factor, prime minus j minus 1, still super exponential. What's interesting is that in the cycle of gaps, the populations of constellations sort out by their length. So let S be any admissible constellation of length j. Its population ultimately grows by factors of prime minus j minus 1. So we see that the populations of all gaps grow by product of prime minus 2 ultimately. Constellations of length 2 grow by product of prime minus 3. Of length 3, populations grow by the product of prime minus 4. And we see the general form. The corollary here is that if we have any admissible constellation S0 of length J0 and pick any admissible constellation S1 of length J1, where that length is bigger than J0, then the ratio of populations of the longer constellation to the population of the shorter constellation will go to 0 eventually. Every shorter constellation eventually outnumbers every longer constellation in this specific way. So we divide away the super exponential growth, same strategy. Here we divide away by the factor prime minus j minus 1. And this normalizing factor is dependent on the length of the constellations we're studying. We get these relative population models. When we look at the eigenstructure, the dominant eigenvalue is now 1. The subdominant eigenvalue, which becomes the parameter for us, is prime minus j minus 2 over prime minus j minus 1. And then the other eigenvalues are shown there. We end up with the expansion for the relative population of the constellation. It's this asymptotic value minus coefficient times the next eigenvalue plus coefficient times the next eigenvalue. And these coefficients come by applying the matrix of left eigenvectors to the populations and the initial conditions for that initial cycle. Corollary here is that every admissible constellation S of length j arises and persists with asymptotic relative population of these products. The product from Q up to j plus 1 of Q minus nu times the product for larger primes that divide that Q. Remember, Q was the product of primes that divide a span between boundary fusions within a constellation of Q minus nu over Q minus j minus 1. That first product really enforces admissibility. Over that product, we have more fusions than we have copies replicated in step R2. And so in order for a constellation to be admissible and to survive, we need the fusions to double up and leave at least one copy, spare a copy for the next cycle. Then the second product really determines the relative growth uh, in a stronger sense. That once we're beyond, we know the constellation will survive. There are more copies than fusions in this range once Q is bigger than J plus 1. For different constellations, these factors will only vary by the divisibility amongst those primes dividing the spans within the constellation. So note the role of J here, the length J. We can study the relative populations amongst constellations of a given length J, but we cannot meaningfully compare those relative weights across lengths. When we're talking about the relative population models, they can only be compared among constellations of the same length. Remember, every longer constellation's population divided by the population of any shorter constellation goes to zero as the sieve continues. Let's look at a couple of examples. Here we have the models for a set of constellations of length 2. So that top curve is for the constellation 6-6. That light blue curve is for 6-12. The dotted blue curve is for 12-12. We again see the constellations of length 2 sorting out into families based on the factors that divide that Q. So we again look at a section. Here we'll take the section across this family of curves at 0.36, and when we take samples in the intervals of survival corresponding to that value, we sample over constellations of length 2. Here we group them by their symmetric pairs. So those first two columns, we put the counts of the constellation 2-4 next to the counts for the constellation 4-2, and then 2-6 and 6-2. That tall column in the middle is the constellation 6-6. And so here we have to look at the symmetric pairs. The symmetric pairs generally agree. There are small differences, and the heights of the columns are in alignment with what the models would predict. Here's a different way of looking at the populations of constellations of J equals 2 over those intervals of survival. We make a heat map. Here the columns are labeled by the first gap in the constellation, and the rows are labeled by the second gap. And we have darkened out the positions for the inadmissible constellations. Those counts will always be 0. We zoom out here to take a broader view over those intervals of survival for these counts over constellations of length 2. Here are some of the models for just a few constellations of length 3. Again, we see the sorting into families by the prime factors of that product Q for each constellation. And then taking that same section, we look at the populations of the constellations to the level that would be predicted by a uniform distribution over the relative populations. And we get pretty good alignment to first order. Here some errors are definitely showing up if you look out toward the right-hand side. So what we've done at this point, we've looked at constellations of length J. We've repeated the process that we went through for gaps. We have the population models. We normalize those to get the relative population models, and we've begun to look at comparisons to data samples from the intervals of survival. And here we see those comparisons do get a little bit more delicate. Thank you.